So we are now in the last couple of sections of Chapter 9. We're going to start with 9.15, and then we'll do 9.16. This is a long chapter. So we'll find that thiols and sulfides are sulfur analogues of alcohols and ethers, respectively. So a thiol is just like an alcohol, except it's got sulfur instead of oxygen. And the sulfide, thiol is just like an alcohol. The sulfide is just like an ether, again, except it has sulfur instead of oxygen. So a couple of important differences. The pKa of this hydrogen is a little bit lower, meaning this is a little bit more acidic. All right, so that's we learned that back in acid trends early in the semester. The other thing that is kind of interesting is that the sulfur is much bigger than the oxygen, and that can have some interesting impacts on how reactive it is. And we'll talk about that here in just a few minutes. Now, the main point of this chapter is not about sulfur-containing compounds, so this is just one section. It's kind of interesting, and that's why I'm putting it in here. So thiols, which are also called mercaptans, so thiols are like this. They have SH instead of OH. And one interesting thing is that the thiols are incapable of intermolecular hydrogen bonding. Hydrogen bonding has to have a hydrogen covalently bonded to oxygen, nitrogen, or fluorine, in this case, oxygen with the ethanol. And sulfur does not count. And so because that sulfur doesn't count, we don't get the hydrogen bonding effect. We just get the regular dipole interaction. All right. So one interesting thing about mercaptans is that they have a very strong odor. All right, and according to a Google search that I did, the word mercaptan comes from the fact that sulfur compounds, mercaptans, are really good at reacting with mercury. So mercury, they were good at capturing the mercury, so they were called mercaptans. So quite literally, mercury captivators, so to speak. The sulfur makes pretty strong bonds with mercury. It also makes good bonds with gold, but they didn't call them gold captans. They called them mercaptans. So interesting, very similar electronegativities between mercury and sulfur, also between gold and sulfur. We want to look quickly at the thiol nomenclature. I don't have any in-class assignment questions on that, but it is pretty easy to use. Thiols are named in a very similar way to alcohols. We use the suffix thiol instead of -ol, and you'll also notice that we put the full name of the parent chain. We don't remove the E from the end, and then we just add the word thiol to the end, and then we number it just like what we do with alcohols. So instead of this being pentan 3-thiol, it's pentane 3-thiol. We're going to leave that E on there. But otherwise, the naming is just like what we see with alcohols. On this one, the SH is on carbon number 2, so we have the thiol, the 2-thiol there. And then here it is 4-methyl, so 1, 2, 3, 4. Yeah, 4-methyl hexane 2-thiol. And then on this one, we've got the 2-methyl cyclohexane thiol. We don't have to number the thiol on this because it's in the parent name. It's assumed to be 1. When it comes to the preparation and reactions of thiols, it's pretty easy. Thiols are prepared via a SN2 reactions quite easily with alkyl halides. So much like what we saw if we took a hydroxide and reacted it with an alkyl halide, we would get an alcohol. In this case, we react it with hydrogen sulfide ion, and we will get the thiol. And you better do this reaction in a hood, or you will have lost a bunch of friends. If you want, you can take thiols and oxidize them with bromine or iodine, and when you oxidize them, you will end up getting disulfides. And if you want to take a disulfide and break that apart, you just use zinc and HCl to reduce the disulfide back to the thiols. So these disulfide bonds actually end up they end up happening quite a bit in proteins. So when you do stuff like when you break apart some of those proteins, sometimes you'll get these really foul thiol smells. All right, so sulfides are named in a similar way that ethers are named, which is that we just take the suffix sulfide and as a separate word, and then we put the names of the alkyl groups that are attached to that sulfide on either side. So this is diethyl sulfide over here. If we have an unsymmetrical, we just do it alphabetically. So sec-butyl ethyl sulfide would be the case there. All right, so sulfide synthesis and reactivity. The sulfides are prepared from thiols by an SN2 reaction, analogous to the Williamson ether synthesis. So we deprotonate with something like sodium hydride, and then that will give us this sulfur nucleophile, reacts with an alkyl halide, and we can form sulfides. Now, one interesting thing about sulfides, there's lots of interesting things, but one I'm going to point out just real quickly is that these sulfurs in sulfides are actually still pretty good nucleophiles. We don't normally think of like ethers as being good nucleophiles, but sulfides are good nucleophiles. And so if you take a sulfide and react it with a sterically unhindered alkyl halide, you will get alkylation of that and form a sulfonium ion. And we'll talk about onium ions at a later point in the second semester. But that's an interesting reaction and something that is not, that we don't see that with the oxygens. So we just don't see this kind of reaction where we have 3 carbons bonded to an oxygen. It just doesn't happen. All right. So now we want to look at the last section, and the last section is important. This will be looking at reactions of epoxides. So reactions of epoxides, and we're going to start with the fact that epoxides don't have a good leaving group, but that does not stop them from reacting. Epoxides are pretty reactive. All we need is a good nucleophile, and we can get the reaction to occur. So there is a strained 3-membered ring. We talked about this earlier. These are sp3 hybridized carbons and oxygen, and the typical angle for sp3 comes out to 109.5. However, we will find that this is restrained to about a 60-degree angle. So whenever we break open that ring, we relieve a lot of angle strain, and that releases energy. So if we have a decent nucleophile, a pretty strong nucleophile, come in and react with one of those carbons, those electron-poor carbons, we can open up that ring even though alkoxide is a poor leaving group. So that is one way we can do that. So let's look at adding nucleophiles to epoxides. So nucleophilic addition to epoxides can occur pretty readily with strong nucleophiles with acids like HZ, where Z is a nucleophilic atom. For example, chloride, bromide, iodide, those are all fairly nucleophilic. All right, so here if we've got a strong nucleophile like cyanide, the cyanide can come in and react with one of these. It's going to react with this one in this case, but it'll give you the same thing either way. It will break it open, and then in a second step, we're going to add water, and that water will protonate the alkoxide to give us the alcohol. So we'll get our nucleophile on one carbon and OH on the other carbon. If we have an acid like HCl, HBr, HI, and those kinds, we will protonate this, and then the chloride will come in and react with one of those carbons. So we'll have OH on one of the carbons and the halide on the adjacent carbon. We can do the same thing with water, and we can also do the same thing with an alcohol to make an ether. So let's look at number 70. We'll look at number 70 on the in-class assignment. So here is our document camera. All right, so ethylene oxide is just the simplest epoxide. So it's just simply that epoxide. So again, we're going to have OH on one of the carbons and then whatever the nucleophile is on the other carbon. So in this case, we will end up with OH on that carbon and bromide on that carbon. In the case of water, the water will add H2O, but it'll deprotonate, so we'll get OH. So in this case, we're going to get OH on both of the carbons. And so that is ethylene glycol. So ethylene oxide, or oxirane, will react with water and sulfuric acid to give us ethylene glycol. All right, here we've got ethoxide ion, and so we'll get CH3, CH2. That will react with carbon, and then OH. All right, now we could have drawn this. This is equivalent to doing it this way. 1, 2, 3, 4, OH. All right. With this one here, our nucleophile is the acetylide ion. So we'll have H, C, triple bond, C, and then CH2, CH2, OH. So again, OH on one and the nucleophile on the other carbon. All right. Here on hydroxide, this is going to do the same thing that this one did, except it's going to do it under basic conditions. So we'll get OH on one of the carbons and OH on the other carbon. So again, we are going to get ethylene glycol as our product. With this one, we've got CH3S minus as our nucleophile, and then we'll protonate. So we'll have CH3S and then OH, and that's going to give us our product. And in case you're curious, that's equivalent to this. If you wanted to draw it without putting any of the CH3 in there. All right, so that is number 70 on our in-class assignment. So we want to look at the mechanism for epoxide ring opening because it's a little bit revealing. Virtually all strong nucleophiles will open up an epoxide ring using a two-step reaction sequence. So if you add a strong nucleophile and then you add water in a second step. First step, strong nucleophile will react with one of the electron-poor carbons in our epoxide. So the nucleophile will attack one of those electron-deficient carbons by SN2 mechanism. So here it doesn't particularly matter which one it goes to, but it'll attack it by an SN2 mechanism. It'll pop it open, and that will give us the alkoxide. Well, that alkoxide, we then add water. It will protonate that, and we will end up with this alcohol. So we'll have CH3O, CH2, CH2OH. All right, so we protonate it with water in that second step. When it comes to the stereochemistry of epoxide ring opening, unsymmetrical epoxides, the nucleophile will attack the less substituted carbon. So here we've got this unsymmetrical epoxide, and you'll see that we've got one carbon has just 2 hydrogens and the other carbon has 2 methyls. So this one is less substituted. Because it's an SN2 reaction, that nucleophile will go to the less substituted carbon. It will break open that, form the epoxide or the alkoxide, and then of course we can protonate with water to give us that as an alcohol. All right. If we have a meso compound, for example, with this compound, it is a meso compound. Remember, meso compounds, they have at least one stereogenic, they have actually at least 2 stereogenic centers, and they have a plane of symmetry, so they are achiral. And so this molecule is achiral, even though there are 2 stereogenic centers there. But you'll notice there is a plane of symmetry that goes right down the middle of that molecule. We get nucleophilic attack on that carbon. If it attacks the top carbon, we'll get this first compound A. If it attacks the bottom carbon, we will get the second compound B. These 2 compounds are enantiomers, and so we will get a perfect racemic mixture of these 2 compounds. So the enantiomeric excess will be 0. We'll have exactly the same amount of A and B. Just as a reminder, enantiomers are stereoisomers that are mirror images of each other. So these 2 molecules are mirror images of each other. Okay. Now this is something important, and so I want to emphasize it again on another page here. If you start off with an optically inactive compound, like this meso compound that's on the left, you're always going to have an optically inactive products. That doesn't mean you have achiral products, it means you have optically inactive. And so if you have a 50-50 mixture of enantiomers, that is going to be optically inactive. So if the alkoxide, methoxide in this case, reacts with that top carbon, we will end up with this as our intermediate, and then we'll protonate that to give us this alcohol product. If the methoxide reacts with this bottom carbon, again from the back side of that, we're going to get this, and we'll get this as our product. And we will get, as I mentioned, a 50-50 mixture of these 2 products. So achiral starting materials will have to give you a racemic mixture of these 2 enantiomers. When we're doing acidic epoxide ring opening, our first step is going to be to protonate the oxygen on the epoxide. That makes it a good leaving group, and therefore you don't need as good of a nucleophile. You still want a good nucleophile, but it doesn't need to be quite as strong of a nucleophile as some of the other things that we were just looking at. So we protonate it. That makes this a good leaving group. The nucleophile comes in and reacts with, it will come in and react with one of those carbons and open it up, and we will get this. So nucleophile opens up the ring via backside attack. Again, it's still SN2. It's still SN2. However, something interesting happens. Even though it's SN2, something interesting happens when we have unsymmetrical. We'll look at the unsymmetrical ones in a minute. Hold on. All right, so here are just a couple of examples of doing this. HCl, HBr, HI, they will open it up to give us this. Right, so we'll get bromine on one, OH on the other. And then if we use water and sulfuric acid, we will get 2 hydroxy groups. So we'll get a diol that is trans. We will get a racemic mixture of these because we're starting off with an optically inactive starting material. So we have to have an optically inactive product. So they would be racemic mixture. If we use an alcohol, we can form ethers. So we use alcohols, we can form ethers. So there's all kinds of interesting things we can do. When we're doing this on rings, we're always going to get these trans disubstituted cycloalkanes. Okay, so for acidic epoxide ring opening, when it's unsymmetrical, all right, so let's say we've got this 2,2-dimethyl oxirane, and we protonate in our first step, and so now we've created a good leaving group. Well, something kind of interesting happens. When our nucleophile comes in, we'll find that there's going to be some partial positive charge on this carbon. And that's because these two alkyl groups help to stabilize it, and it puts a little bit of partial positive charge on that carbon, and therefore it makes that carbon more attractive to our nucleophile. So even though it's more substituted, the nucleophile is going to go to the more substituted carbon. So you'll end up with the nucleophile going to the more substituted carbon. That's even true if it is a tri-substituted carbon. So you can get SN2 reactions happening at tertiary carbons, which we haven't had that before. So, all right. And so here in our transition state, we get a little partial positive charge on that carbon. That lowers the transition state energy and makes this pathway much more favorable. We just don't see any of the nucleophile going to the less substituted carbon, which is just really, really unusual for SN2 reactions. But it definitely is an SN2 reaction. When it comes to the regioselectivity of epoxide ring opening reactions, here is the selectivity. So here we can add the same thing to this epoxide, but if we do it as a strong nucleophile, that strong nucleophile will go to the less substituted carbon. And if we do it as a weak nucleophile with acidic conditions, then the nucleophile will go to the more substituted carbon. And that is a cool trick. And we're going to look at that in number 75. We're going to take advantage of that here in number 75. So let's switch over. Here is number 75. All right. So here we are. This is acidic conditions. This is our nucleophile. Ultimately, we will deprotonate this, so we're going to add CH3CH2O to this, and because it's under acidic conditions, that nucleophile is going to go to the more substituted carbon. So our product here is going to be OH and then O. So there is our nucleophile, and I'll go ahead and draw these. There's the methyl and the other methyl. All right, so that would be our product for this. Now, if we have the strong nucleophile, it's going to go to the less substituted carbon, so it's going to go over here. So O, CH2CH3, OH, and then the methyls are there. So we get two very different compounds depending on whether we do acidic conditions or basic conditions. Let's do another one. This one is under acidic conditions. So again, acidic conditions, the nucleophile is going to go to the more substituted carbon. So bromine goes there. And then that will give us that particular compound. And then if we use the strong nucleophile, the strong nucleophile is going to go to the less substituted carbon. So CN, OH, the alkoxide gets protonated in that next step. And I'm not doing this consistently, but there's another methyl there. So two methyls there. And so again, that gives us control over that. Well, that represents the end of Chapter 9. And so stay tuned for Chapter 10 coming up soon. And that will be it.